In this example, we'll look at the convergence or divergence of the series -1 to the k plus 1, k to the k. And so this is an odd series, and we have to be a little bit careful with working it out. We can tell that it's alternating. It is an alternating series with the -1 to the k plus 1. As an alternating series, we should be thinking, does this decrease? Is it non-increasing? This is not an obvious thing. If you wanted to turn this into x to the 1 over x and take the derivative, you have to be very careful, and it's tricky to do. But I just want to convince you that, in fact, the sequence k to the 1 over k does decrease. If I looked at 1 and then I looked at 2, 2 to the 1/2 is the square root of 2. So we're looking at the square root of 2, and we're looking at the cubed root of 3, and the fourth root of 4. If you would just plug these numbers into your calculator or plot them, you'll see that they, other than at the very beginning, if we look at the square root of 2, they're going to go down after that. They are going to be decreasing, at least after the very first term. And it is true. This series, k to the 1 over k, is non-increasing. In fact, it's decreasing. Non-increasing after k equal 1. Right, so from 2 and beyond, it is a non-increasing series. So as a non-increasing sequence, a decreasing sequence in fact, with an alternating part with it, all that we care about is the limit. We'd like to investigate the limit as k goes to infinity of k to the 1 over k. And that k in the exponent should remind you of our use of the natural log when finding the limit. What I'm really going to do instead is find the limit as k goes to infinity of the natural log of k to the 1 over k. And by doing that, I can bring the 1 over k down front. This is the limit as k goes to infinity of 1 over k times natural log of k. Plugging infinity in, this is 0, and ln of infinity is infinity, so that's 0 times infinity, but we can just do one very simple trick to make it into a fraction, ln k over k, and by doing so, now it's infinity over infinity. And so we can apply L'Hopital's rule. Take the derivative of the numerator, that's 1 over k, so we're looking at the limit as k goes to infinity, of 1 over k for the numerator, and 1 for the denominator. Well, that's just the limit of 1 over k, and as k goes to infinity, that is 0. But since we've used our natural log at the beginning, the final answer is actually e to the 0, to undo the natural log that we've done, which is 1. So the limit of the non-alternating terms is 1. Remember, for an alternating series, as long as it's decreasing or non-increasing, if the limit of the terms is 0, then it is convergent. These terms don't even go to 0, they only go to 1. So really, actually, by the divergence test, remember the divergence test from a little bit back, the divergence test says if the terms go to anything other than 0, then the series itself diverges. The terms must go to 0, that's not enough. But if the terms go to 0, then we can at least continue. If they don't go to 0, then we're done. If they don't go to 0, the series diverges.